Here is an introduction to spectra to accompany Chapter 5 of the textbook Astronomy from Open Stax. So a spectrum, if you're talking about one object, or spectra if you have many spectrums, this is basically just the intensity of light over a range of wavelengths. And so this beautiful picture shown here, this is the spectrum of the sun in the visible wavelengths. The sun, as we covered in the introduction to light, it's like every other thing. It's a black body. It emits wavelengths of light across the electromagnetic spectrum, right, with different intensities. Here we're just focusing on the intensity of light in the visible region, and it's wrapped around in a way that you go from longer wavelength, and then you read it kind of like a book, to shorter wavelength, and you wind your way down. So you go from the longer red wavelength down to the shorter wavelength that's blue. And if the spectrum were just red to blue continuous, that would be a continuous spectrum. But instead you see lots of interesting features here, right? These gaps where there's no light. These are absorption lines, as we'll cover in a moment. But this, in its essence, for our purposes now, this is a spectrum. This is a stereotypical spectrum. And if you have, gaps in a nearly continuous spectrum, these are called absorption lines. So this comic is a joke here, but this is actually mostly true. This is what in the sun, when you look at the visible wavelengths, you see a continuous spectrum, and then you see some gaps, and it's mostly due to these elements that are labeled here. So those are absorption lines. That's an absorption spectrum. If instead you see an object where instead of having a continuous, like a lot of light at many wavelengths, except for a few gaps, if instead you only have light at a handful of very specific wavelengths, this is known as an emission spectrum. And we'll talk about how these two come to be in a little bit. So note that the presence of the lines, this has to do with the atoms and the molecules in an object. Though in this brief introduction, we'll just focus on the atoms. The concept is very similar for molecules. So before we talk about how atoms can lead to these absorption and emission spectra, we need to take a brief detour and just talk about what an atom is. So an atom, you might have heard it referred to before as a fundamental building block of nature. That's close enough to true for our purposes here. What you basically have is a very tiny positively charged atomic nucleus at the core, and this is surrounded by electrons. We'll often think of this as kind of a cloud of electrons. And we say a cloud because the position is described by a probability distribution. So atoms are quantum mechanical objects. An electron in an atom, you can't really localize at one position at a given time and determine its energy or its momentum that it has. So instead, we think of it as really just a kind of probability cloud of positions. So here you're looking at the hydrogen atom. These are different configurations that it can have, and the colors, the colored regions, these basically indicate the probability distribution for our electrons inside the hydrogen atom. Now, for our purposes, we're going to ignore this very precise quantum mechanical view, and we're going to instead use what's called the old quantum mechanics view, or for the atom, this is the Bohr model of the atom. So an electron, instead of being described in a probabilistic manner that gets a little bit complicated, instead our electron, like one electron is a blue circle here, it orbits the atomic nucleus, which is the red circle here, orbits that in a nice neat circle at some fixed radius from the center of the nucleus. This turns out to be wildly incorrect, but it can give you a lot of useful information. It's still a useful picture of the atom. Keep in mind all theories are wrong. Some are just more wrong than others. So regardless of what picture you use, your atom here is mostly empty space. So This picture here is not to scale at all. Um, your electrons, these typically span some extent that's on the order of a so-called angstrom. So an angstrom is 0.1 nanometers, which is, as you know from SI prefixes, is about 10 to the minus, or is exactly 10 to the minus 10 meters. The atomic nucleus in the center, this is only something called a femtometer, 10 to the minus 15 meters. So your atom's really mostly empty space. A lot of what we think of as an atom is this probabilistic electron cloud, and then the nucleus is just this little tiny dude at the center. So the atomic nucleus itself, this is a group of protons and neutrons. Again, the positions here are actually described probabilistically, but we don't need to worry about that here. Just for our purposes, we can go ahead and pretend that a proton is a little ball hanging out and a neutron's another one, and you have a bunch of these things sitting around each other, and then orbiting them in circles are electrons that are also little spheres. That's a perfectly fine picture for our purposes for this class. So the protons in the atomic nucleus, these provide a positive charge, and the neutrons are neutral. And so typically for a neutral atom, you're going to have some number of protons, and you're going to have the exact same number of electrons. So when the number of protons in the nucleus equals the number of electrons orbiting that nucleus, so in the atom, then you have a neutral atom. You can be missing some of these electrons, and then you have a positively charged atom that's called an ion, that we'll talk about in a little bit. So the number of protons in your nucleus, or in your nucleus that's inside your atom, this defines the element. So for instance, if my nucleus has 1 proton, that's hydrogen. If you have 6, you're carbon, 8, you're oxygen, 50, that's the element tin, and so on. And the number of neutrons, that defines the isotope of an element. So for instance, if I have, let's just say 1 proton and 0 neutrons, that's just hydrogen. If I have 1 proton and 1 neutron, that's called deuterium. 1 proton and 2 neutrons, that's called tritium. Or for most of the other elements, we don't have cute names for them. If I take helium, for instance, and I have that's 2 protons, and I have 1 neutron, we typically call that helium-3, because I take 2 protons plus 1 neutron. That one turns out also to be called the helion. It has a name. But in any case, there are many isotopes of a given element. We'll talk about this a bit later, just very briefly, when we talk about element formation in the universe later on in the class. And to understand spectra, we have to delve a little bit deeper into the atom, and let's just talk about quantization of energy within an atom. So you've heard the phrase quantum mechanics many times. What does the quantum refer to? This indicates that at our smallest scales in nature, where quantum mechanics applies, nature only allows discrete configurations of matter. So that you're only allowed to have configurations of matter that have an energy value or a binding energy that corresponds to specific values. So the energy of the bond of an electron to a nucleus within an atom, there can be many different values of this, but there are only certain discrete values that are allowed. So an electron in a hydrogen atom, for instance, cannot be arbitrarily bound to the proton in the nucleus of that atom. There's only discrete energies that you can have, and these are known as excited states, or also energy levels. And in the Bohr picture of the atom, we'll represent these by circles of different radii. So the really tight circles here with the small radii, these are very bound electrons. There's a lot of energy holding these electrons into the atom, and you get to less bound electrons as you move out to larger radii in these cartoonish picture. And these are different energy levels here. An electron, a given electron can move from one energy level to another by absorbing or emitting a photon. So for instance, if my electron starts out at this higher energy level here, and you de-excite to a more bound energy level, then a photon can carry away energy. And the amount of energy that is released is directly related to the difference between the two excitation energies of these states, as we'll talk about in a moment. So if an electron goes from one of these higher energy levels to a lower one, that's called de-excitation, and a photon is emitted. But the inverse process can happen where instead a photon could be absorbed and cause our electron to be excited from an inner orbital to an outer one, and that's a process called absorption. The frequency of the photon connecting any two energy levels is given by this equation here, where the energy of that photon is equal to h, which is Planck's constant, times the frequency of light. Planck's constant is roughly 6.6 times 10 to the minus 36 joules times seconds. So when we multiply this unit, joules times seconds, times a frequency, which has the units of hertz, which is 1 over seconds, then the seconds here cancels with the 1 over seconds from the hertz, and you just get something that's joules, and a joule is a unit of energy. You can see from this equation that a higher frequency, that, as we know from the introduction to light, corresponds to a shorter wavelength, and from this equation, that higher frequency also corresponds to more energy. A lower frequency is a longer wavelength and is less energy. And so, for instance, if you look at typical wavelengths of given parts of the electromagnetic spectrum, you can see that an X-ray carries about 1 billion times more energy than a radio wave. Okay, right? And this is why we are worried about X-rays in terms of the damage that can be done to our body from them, but we don't really care about radio waves, right? This is why, for instance, a cell phone or 5G is not going to melt your brain because radio waves have very little energy, whereas, you know, when you get X-rays, for instance, at the doctor's office, you want to limit how many times you do that because there's a lot more energy in those photons. So now we can see, based on these the quantization of the energy levels in an atom, we have a natural picture to explain our atomic spectra, to explain these absorption and emission lines. So connecting certain energy levels will give you a given wavelength, and you can either, for instance, have a longer wavelength connection here, give you, for instance, purple light, or you can have another one here that gives you red light. So it just depends on the energy difference between these two energy levels. So in this case here, you have a very large energy difference, and so that's going to be higher frequency light. Right, here's a smaller energy difference. It's going to be lower frequency light and a longer wavelength. And so, given the atom that you're looking at, you're going to have different values for the energy levels, and so therefore you're going to have different absorption, or in this case, emission lines. So, within a given atom, you have different energies that can happen, different photon energies, because you can connect, for instance, one excited state to another, or a different excited state to that same excited state, in this case the ground state. So a single atom, you can have many different photon energies from that, but also these energy levels themselves will have different energy values for different atoms. Okay, so that's why these, in this case, emission spectra are very different when you go from one atom to the next. And you might wonder, if you have many more electrons in like sodium, why are there not that many more lines than hydrogen? Keep in mind, what's shown in this picture are just the visible lines. You can absorb or emit light across the electromagnetic spectrum, to some extent, and so we're not seeing everything here. The visible is a very small chunk of the electromagnetic spectrum. And when you look at what we typically call a neon sign, these are these gas filled, these signs that are filled with noble gas, and energy is pumped in there, and then that energy is re-emitted from the atoms, and you see a different color. Really, only the red signs are actually neon. The others are different. The other colors are different noble gases when you look at those. So just focusing for a moment on the hydrogen atom, because this tends to play an important role in astronomy because the majority of the universe turns out to be made of hydrogen. We can look at specific wavelengths that are emitted in the hydrogen atom from de-excitation or absorbed from absorption. And we call these series. So a series, it basically groups together excitations from or de-excitations to a particular energy level. So for instance, anytime an electron de-excites from an excited state down to the ground state, this is the lowest energy state, that is known as the Lyman series. And so if you de-excite and emit a photon, that is the Lyman emission series. If instead you were to absorb energy and leave the ground state and go to some other excited state, that's the Lyman absorption series. But you can see any things that connect the first excited state. This is the Lyman series. Then you get the Balmer for the first excited state, Paschen for the second excited state, and many of these have different names. It keeps going, and you could look at these for the wavelength of light, and you can see, for instance, your Lyman has this very short wavelength here. The Balmer is a somewhat famous series because this is in the visible, and Paschen, you're getting out in infrared, and so on. There are many more series here. And just to remind you how these can come to be in an astrophysical environment, you can, for instance, heat up a really hot, you can heat up some object, for instance, a cloud of gas, and that can de-excite, so the energy absorbed in terms of photons can be emitted from the atoms in this cloud of gas, and that will give you emission spectra. Or you could have a really hot object here, something like a star, that gives a mostly continuous spectrum, and that spectrum will be modified by the light passing through a cloud of gas. Photons of very specific frequencies will be absorbed, and you'll be left with this absorption spectrum here, where you have something that looks continuous but with some gaps in it. So this is basically the microscopic picture of how you get the absorption and the emission spectra. It just has to do with what are the atoms that you have in an object, and are they hot and de-exciting, or is it just being absorbed? Is the photon being absorbed on the way through, and so you don't see it on our end when you're observing? Now, besides these excitations and de-excitations, I just want to briefly note you can also have atomic ionization. So an ion, this is just a charged atom. So that means your number of protons in the atomic nucleus is not equal to the number of electrons that are orbiting that atom. So ionization, this is the process of removing one or more of the electrons from the atom, and that changes the atomic charge. So the amount of energy that it costs to remove an electron is going to, first off, depend on the atom. So here we're looking at removing the most bound electron from a given atom. So that's the vertical direction on this graph, versus the atomic number, so the number of protons in the nucleus. Or you can think of it as the number of electrons in a neutral atom of that particular element. And what's interesting here is you see a kind of sawtooth pattern, right? The ionization energy goes up and then chops down and then up and chops down and up. And you may notice that the peaks are the noble gases. And what you're looking at here are the rows of the periodic table. And so this is the first row, second row, it ends here. The third row ends here, fourth row ends here. And so the ionization energy is going to be, linked to atomic structure, which is not particularly surprising considering what we just talked about in terms of the absorption and emission spectra. Now, the amount of energy to remove an electron is not only going to depend on the atom, it will also depend on the energy level that the electron is in the atom. So we can take the case of hydrogen. If your electron is in the lowest energy state, the one that's most bound, we call the ground state, you have to input 13.6 electron volts of energy in order to liberate that electron from the oppressive clutches of the hydrogen atom. If instead your electron is at an excited state, for instance this one here, it only costs 1.5 electron volts, much less, to ionize that. And how can this ionization happen? One way for it to happen is a photon being absorbed. Now, you can also have two atoms collide. That brings in energy as well, and that can also cause ionization to occur. And just want to note, why am I talking about this? Why do we care about this? It's interesting in astrophysics not only to give you a composition of the environment. You can use absorption and emission lines to figure out what atoms are present in the environment. What is it made of? What's the atmosphere of a star made of? What's a cloud of gas made of? But also, you can use this information to figure out the environmental conditions, the temperature and density of that environment, because the fraction of a given atom that's in a given ionization state is a direct indicator of the environmental conditions. Same for the excited state. So I can make a plot here of the amount, the number of atoms, or the fraction of atoms that are in a given state versus the temperature. And we can see, for instance, that calcium, very little calcium is ionized when you're at 1,000 or a couple thousand Kelvin. And as you get up to solar temperatures, so around 6,000 Kelvin, most of the calcium is ionized. And this is why calcium lines feature prominently in the sun, is that you've mostly ionized it, you're absorbing photons at the wavelength that correspond to ionizing calcium. And the fraction of atoms is going to depend, sensitively on the temperature. So you can see in this case, the calcium atom is a very sensitive indicator of the temperature between a couple thousand Kelvin up to around 7,000 Kelvin or so. And different atoms are going to be sensitive indicators in different temperature regions. So, for instance, for hydrogen, you're looking at something between, let's just say 6,000 or 7,000 Kelvin up to about 15,000. That is a useful atom to learn about the temperature and density conditions. This is getting into the weeds. You don't need to know how this is done. If you really care, you can look into something called the Saha equation, and that allows you to calculate this. If you really want to be able to reproduce this graph, you need to take Astronomy 4201, which you probably won't take ever, but if you change your major, maybe you will take that one day. And that is it for this introduction to spectra for Astronomy 1000.